Hello, everyone, and welcome to our webinar. My name is Bob Cusart, Director of Market Access and Development for APA. I will serve as moderator for the session. I'm excited to say that we have two speakers today, Matt Brown and Stephanie Thomas-Reese. Our topic today is titled Resilient Construction with Engineered Wood Sustainable Code Compliance Solutions. This webinar highlights the role of resilient construction methods and APA engineered wood products in creating stronger, sustainable, and code-compliant buildings, offering essential resources and best practices for designers, engineers, and builders. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood construction systems and educates users and specifiers on the product's proper use and potential applications. Before we start today's webinar, I need to cover a few housekeeping details. This presentation will last about 50 to 55 minutes. Handouts of the slides can be found in the control panel on your screen. To ensure that everyone can hear the webinar clearly, we have muted all participants. While we are bookending the discussion with our cameras on, we will be turning them off during the session to maximize the connectivity of the webinar. During the presentation, we encourage you to submit questions by typing them into the questions pane on the control panel on your screen. We will answer some questions in the chat box, and we will answer some in a Q&A at the end of the session as time permits. A recording of today's program will be posted on our website, apawood.org, in a little under a week. I'd like to note that today's webinar is approved for AIA and ICC continuing education credits. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link to customized certificates of completion. The information provided in this webinar is based on APA's research and field experience, but mention that no warranties expressed or implied are made. APA and its members are not liable for any damages resulting from the use of this information. Users should consult local regulations or a design professional to ensure compliance with relevant codes and standards. APA does not control workmanship quality or usage conditions, so it cannot guarantee product performance or design outcomes. The content is copyrighted, and reproduction for use or for AI training requirements requires written permission from APA. Your feedback is important to us. I would like to point out that you see a QR code on your screen. If you open your camera on your smartphone, a link will pop up to take you to the survey on this session. A link will also be emailed to you about an hour after the conclusion of the seminar. Today's presenters are Matt Brown and Stephanie Thomas-Reese. Matt serves as the Director of Energy Policy and Code at APA, with over 20 years experience in the building industry, including 15 years expertise in energy rating, engineering, and code development. He is dedicated to advancing energy efficiency in a balanced and cost-effective way, integrating both energy efficiency and structural design consideration. Matt holds certificates as a certified green professional, certified zero energy buildings professional, an ICC certified plans examiner inspector for the IECC, and is based in Indiana. Stephanie is located in Florida and is an engineered wood specialist and territory lead for APA. She is an experienced designer and energy professional with a bachelor's degree in architectural design from Clemson University and a master's degree in energy efficient building from Oxford Brookes University. She has over 25 years of experience in building science and research and is the co-author of EcoHouse, a design guide which has been published in 4 editions, 6 languages, and provides design information about the latest low-impact materials and technologies in homes all over the world. For those of you just joining us, welcome to our webinar, a renewed focus of resiliency using engineered wood products. We will now turn our cameras off, and I will turn the presentation over to our first speaker, Matt Brown.
Thanks, Bob. We are happy to have you in attendance for our session today, a renewed focus on resiliency using engineered wood products. This is our course description that we'll be talking about during today's presentation. We'll discuss the newest initiative at APA and the industry as a whole in building more resilient structures that are admittingly being exposed not only to natural disasters that are increasing in number each year, but intensity and frequency as well. So for today's objectives, we're going to be looking at defining and explaining the importance and advantages of resilient construction methods promoting health and wellness in communities. We're going to look at outline APA's resiliency focus. We're going to discuss code requirements, standards, and certification programs, and identify design and construction techniques using engineered wood products. So for today's agenda, we're going to hit 6 main topics. And the first one is going to be why. We're talking about resiliency, the definition, the pillars of the resiliency as APA sees it, how with APA resources, examples of the good and the bad, and APA moving forward. We're going to start with the why. Everyone knows today that extreme weather conditions in various parts of the world are the result of climate change and global warming. It's not just the number of heat waves, heavy rainfall, and major hurricanes that have increased in the world, but the strength and intensity of these events has increased considerably as well. Architects, engineers, and builders are at the forefront of going beyond existing design practices. They are using innovative strategies to promote structural sustainability and safeguard occupants. Various strategies, such as utilizing durable and low-carbon materials, incorporating passive cooling techniques, and integrating nature-based solutions. Investors are aligning their portfolios with sustainability goals. Resiliency includes energy efficiency, which the codes are mandating. In fact, energy efficiency is one of the top codes in the biggest priorities to incorporate into new homes. Looking at hurricane strength and frequency over time, you can see that it has increased in strength and intensity since the mid-1990s. This is a pretty telling graph. It's very interesting. So now that we've talked about the why of resiliency and why we're paying attention to it as APA, let's talk about APA's definition of resiliency. So APA's definition of resiliency is the ability to design and construct buildings that can withstand and recover from severe wind events, seismic activities, fire, and floods while promoting sustainability and energy efficiency, utilizing engineered wood products. This is achieved through APA's 4 resiliency pillars: structural resilience, hazard mitigation, sustainability and stewardship, and energy efficiency. Now that we've talked about the definition, we're going to move on to talking about the 4 key pillars that APA sees as part of our definition of sustainability. So as communities worldwide have been struggling with the effects of climate change, resiliency is becoming more and more important and a more prominent topic when we talk about codes, code development, and building of buildings and homes. Our resiliency pillars include the following. 1, structural. Structural resiliency is very important. Hazard mitigation, making sure that the building can withstand fire and floods where appropriate. Sustainability and stewardship, making sure that we're doing sustainable items or putting sustainability policies in place for the built environment. And energy efficiency, a core piece of a solid resiliency plan to make sure the building is energy efficient and survivable after a major disaster. So first today, we're going to talk about structural resilience and the importance of a structurally resilient structure during high wind and seismic events. So the key to structural resilience is promoting resilient, high-performing buildings that are capable of withstanding severe wind events. Seismic resilience is advocating for high-performance seismic design and construction of new homes and buildings. So first, we're going to talk about high wind and wind. And APA has several resources for this, and we'll talk more about them later on in APA's resources as well. But we have brace for high wind events and maximizing wall bracing using wood structural panels for continuously sheathed walls. And on the seismic side, we'll talk about wall bracing for seismic. We're also going to talk about force transfer around openings. That's a solution that APA has for seismic. And weights of materials come into seismic design as well, where wood is typically a lighter construction product than some other competitive products on the market. We also see the importance of structural resiliency come up in different programs around the country. One of them is HUD, so they have some guidance for continuously sheathed homes in their community resilience toolkit, as well as HUD's resiliency guide for wind, which basically cites that a complete wrap of OSB or plywood, we call it wood structural panel in the industry on the exterior, is recommended to make sure that you can withstand the wind pressures needed and design a more resilient structure. The other program is Fortified. Fortified has different programs at different levels, but their gold program deals heavily with protection from wind, with fully sheathed homes and other methods that can be utilized to increase the resiliency of the building for high wind events. So when we talk about hazard mitigation, we're going to talk about structural fire first. And to be straightforward, AWC, the American Wood Council, takes the lead on structural and construction fire issues. APA references their resources. This is the way the wood industry and our partners utilize each other's expertises. And they also deal with wild urban-land interface, or WUI, fire codes that we hear a lot about on the West Coast. We have resources that we link to them, and they have resources on their website. But they primarily produce those resources, and APA offers them out in the field as well. For flood, one of the things that APA has out in the market is a promotion for raised wood floor systems. And it talks about the ways in which you can have a raised wood floor with a crawl space. In those crawl spaces for flood, you can have flood dampers and stuff like that that allow the structure to stay, even if the crawl space were to have to flood out in a flood issue, and still maintain a livable condition space. So here are a couple resources from the American Wood Council on structural fire. You can go to constructionfiresafety.org, and it'll help give you a 5-step best practices. And also they produce the fire design specification for wood construction guide as well. APA has several resources for flood and raised wood floors. So we're talking, in this case, a raised wood floor case study for Cooper Homes. And you can also find the raised wood floor design guide that we have. And it was a big promotion in the Southeast after hurricane damage and floods came through. Some foundations down there have flood dampers and stuff like that that allow the building to withstand floods in its direct area. Starting in the late 80s and early 90s, this movement towards sustainable structures began. Green building programs created a quantitative way to evaluate buildings' environmental impact and sustainability. Most recently, in sustainable structures, we have seen a shift in focus towards carbon accounting and the creation of Architecture 2030, the Carbon Leadership Forum, and SE 2050, all focus on decreasing carbon emissions. Now there's a high priority to develop resilient structures against hazards, but to also allow those structures to stay habitable when services are severed and occupants are still there. Green verification reports are becoming more common. APA's green verification reports help building officials and design professionals determine the product's eligibility for points under different green programs. APA issues these reports to document the compliance of engineered wood product that is manufactured under a quality program audited by APA to specific international, national, or industry recognized green building standard. Several of APA's member mills also participate in forest certification programs. So here's a list of a few different certification programs. You can find if the mill is participating in one of these programs on their various mill websites. Life cycle analysis, called LCAs, and environmental product declarations, called EPDs, are becoming more and more common and are becoming required in some areas of the country for construction. As we move forward and more attention is paid to sustainability and carbon and embodied carbon moving forward, both from a codes perspective and a policy perspective, you'll see more and more discussion around LCAs and EPDs. The American Wood Council is charged with maintaining a database for EPDs and getting them online with LCAs as well. This information will be used in future programs in carbon accounting, as well as embodied carbon calculation programs that will be coming forth in the next several years. Energy codes are becoming increasingly important in resilient structures. And part of it is we want to improve energy efficiency and supporting cost-effective updates to energy codes and policies. Another part of that is survivability and the ability to maintain livable temperatures for several days without energization to the house, electric, gas, or other means of producing energy. And another part of that is high energy performance, ensuring that we have high energy performance in our structures today through well-insulated thermal envelopes that can support life and temperatures. APA is developed and is developing more and more resources on energy efficiency. APA's performance-based energy code publication, originally developed in 2016 and revised this year in 2024, is designed to be a guide to start conversations between builders, energy professionals, or designers about material and equipment options that can be utilized in the performance pathway of the energy codes. All homes have to be specifically modeled to that home design and site address, but it gives a starting point for discussions about if I change my walls, what's my impact on energy efficiency? Or if I want to put better windows in or a different heating system, what can be the advantages that I may see as the builder? Performance-based energy code is essentially about looking at all the pieces of the home. Different from the prescriptive path that focuses on a set table of R values in the prescriptive code, it's kind of just a recipe. The performance path looks at putting insulation where it makes the most sense for your most value, and looking at other efficiencies within the home, whether it be windows, tight air leakage, tight HVAC equipment, high efficacy lighting. It takes the entire home as it sits into consideration versus just a checklist approach to energy efficiency. Survivability is a big part of where the energy efficiency portion of resiliency comes from. Because as we've had more and more storm events, we've also had warmer weather or colder weather in some areas of the country due to climate change. And people need to be able to have survivability in their home for a few days without power generation or power to the home. And there are several different programs that talk about the specificity of what that should be. ICC has some, DOE has some, Department of Energy, but they talk about different survivability aspects. And one of the things that they look at is additional insulation, air sealing, preheating and cooling, and phase change materials as part of the product of survivability. We look at it from purely an energy efficiency standpoint and making sure that we have thermal comfort by having a well-insulated building thermal envelope. And some of these programs have incentives for the builders. There are federal tax credits available currently of $2,500 per home for Energy Star version 3.2. There are also federal tax credits available of $5,000 per home for DOE's Net Zero Energy Ready Homes program. And there are multiple utility incentives and state programs, depending on your local state or utility that you're in, that vary anywhere from $200 to $2,800 per home. And some incentivize different insulation products, as well as different furnaces, thermostats, and HVAC equipment in general. There are also rebate incentives to the homeowner through federal tax credits such as the Energy Efficiency Home Improvement Tax Credit, the Residential Clean Energy Tax Credit. There are multiple state utility incentives, state and local energy code adoption incentives as well, and other code and standards adoptions that are locally based that can provide rebates to the homeowner as well. And with that, we finished up our resiliency pillars portion of today's presentation. And I'm now going to pass the presentation over to Stephanie Rees to talk about APA resources.
We're now about halfway through, and we're going to change it up a little bit, and I'm going to be speaking to us. So if we look at the agenda, we're going to discuss the implementation of resilient methods in construction and how APA's resources can help accomplish this. We have a variety of tools to help assess, design, detail, and apply those different approaches of resilient construction. This includes engineering calculators, our publications, we have CAD details, case studies, as well as engineered wood specialists located all over the US and Canada that can provide technical support to architects, engineers, code officials, and builders. So we'll highlight some of these resources and where they are on our website, as well as where the representatives are located that you can contact. A great method for utilizing engineered wood products in shear wall design is FTAO, or force transfer around openings. And if you want to find more information and resources that we have dedicated to this, you would go to our main page at www.apawood.org, and in the drop down under Resource Library, just type FTAO, and this will populate many of those resources. Also, on our home page, in our Design and Build drop-down, under Design Solutions, you can find more resources about FTAO, like our calculator and a webinar about the calculator's use and explanation of the methodology for designing more flexibility in shear walls. As wood frame construction is continuously evolving, designers in many parts of the U.S. are optimizing resilient and sustainable design solutions that require the understanding of force transfer between elements in the lateral load resisting system. And using renewable sources like wood structural panels to accomplish these load path transfer options are a great way to meet sustainability goals. Also, there's case studies and a YouTube video here that conducts an interview with a developer that explained how a 120-unit apartment building in California was value engineered and determined that a switch to I-joist compatible glulam, double-sided wood structural panel portal frames, and shear walls using the FTAO analysis got the project within budget while addressing the seismic loads. And if I can just reiterate, like the case study shows, shear walls designed with force transfer around openings offer advantages compared to other types of shear wall design, like more flexibility, more versatility, because designing with the FTAO allows for the use of narrower wall segments while meeting the required height to width ratios, and a high likelihood that fewer hold downs will be required. We have a wall bracing calculator which simplifies the design of residential structures to comply with the IRC. Wall bracing are structural elements that prevent walls from racking and deforming due to lateral loads from earthquakes and high winds. And in addition to the calculator, there's a video that walks new users through the basics of the APA wall bracing calculator. And this is a free tool that creates printable reports showing 2009, 12, 2015, 18, 2021 IRC wall bracing compliance. And the reports are accepted by most local jurisdictions. Fully sheathing with renewable material, again, like wood structural panels, as opposed to metal bracing or flexible sheathing products, results in a rigid box-like structure with strong, resilient IRC compliant walls. Advanced framing method is another solution to incorporate resiliency in construction. Using continuous wood structural panel sheathing supported at 24 inches on center framing allows builders a cost-effective system that will produce more energy efficiency by allowing deeper wall cavities for insulation, and does not compromise the strength or durability of the structure. Less material and lower labor costs than conventionally framed homes, advanced framing techniques are more resource efficient. APA has several publications, CAD details, case studies, and a webinar that discusses advanced framing techniques, the benefits, and challenges that builders encounter during the conversion from traditional framing to advanced framing. The left image is our advanced framing publication you can download from our website, and the picture on the right demonstrates how properly sizing and minimizing framing material is conserving cost and resources while aligning those framing members, optimizes load path continuity, and enhances structural integrity. If we compare energy alone and look at the R values in different climate zones using advanced framing, you can see larger values in climate zone 2 are partially because the base wall system is an R13 in that market, giving greater value to the 2x6 advanced framing system. Similarly, in climate zones 5 to 7, the base wall system is an R20 plus 5, and that compared to a 2x6 wall with wood structural panel sheathing. So those plus numbers or points means additional energy is used, where in climate zone 2, those negative points denote a reduction in her score by 4 points, meaning more energy savings. Over a 10 to 13 year period, APA followed storms and created individual storm reports that looked at the storm's damage and noted the patterns in those failures. We then identified those common first failure points and determined a threshold that we would base and develop our Building for High Wind Resistance in Light Frame Wood Construction Guide. Now, this guide creates a framework to improve overall performance in the structural shell and focuses on good connection details to tie together exterior walls, roofs, and floors. And it goes through a structure's key load path connections from the top down, as you see from the middle image. Now, the guide creates recommendations that in most cases exceed the minimum code requirements. And you might think that, well, this will ultimately increase cost. But one jurisdiction that adopted this guideline for their minimum code compliance determined that the incremental cost was only about $400 for a typical 1,600 square foot home. And again, strengthening the structural integrity to improve resiliency. We also have a webinar that follows the load path described and shows many of those failure points from each storm and how they should be mitigated either through strengthening or just simply proper installation of what was specified. The idea that less is more is a sustainable way of construction that can help reduce our environmental impact by conserving resources using light frame engineered wood products that are generally more straight, further reducing waste, using mass timber like glulam and composite laminated timber, or CLT, in lieu of concrete and steel that tends to be more labor and carbon intensive. Biophilic design can improve the human well-being by creating healthy, inspiring environments. By exposing the structure when program allows for it, reduces unnecessary materials and highlights the raw structure, and in some cases can become a learning tool. And again, using advanced framing technique meets sustainability goals. I mentioned the case study already, but here's two buildings, one 4 stories over 1 and the other 2 stories over 1 that utilize wood podium rather than a traditional concrete podium. Again, these case studies highlight the following benefits like fewer trades on site, less mobilization time, fewer construction delays, improved framing efficiency, easier field modifications, decreased mass for lateral design, etc. Again, less materials from an embodied carbon superior material equals a sustainability win for projects like these. The use of mass timber for taller buildings has had a large foothold in Europe and Canada for some time. The intersection of lower embodied energy and renewable resources propels the mass timber industry forward. As discussed, timber buildings store carbon in their structure for the life of the building. So an 18-story mass timber building, for example, has a negative carbon imprint equal to taking 2,350 cars off the road per year. According to the contractor of this building, the Ascent Tower in Milwaukee, Wisconsin, while mass timber materials are not inexpensive, they do offer several cost-competitive advantages and long-term benefits, like the columns, beams, and panels on average weigh 1/5 the weight of concrete and steel materials, reducing shipping costs and requiring a smaller workforce to install. Prefabricated panels delivered directly to the job site that allowed construction time to be reduced by approximately 25%, further saving owners more time and money. And again, the biophilic effect that wood structures have on people, like increasing occupants' overall health and wellness. All this gives long-term value to the design. And with the 2021 IBC code change, the U.S. allows up to 18-story tall wood buildings. Here pictured are two examples, an 18-story student housing project in British Columbia and that 25-story apartment building in Milwaukee that I mentioned earlier. This is probably one of my favorite designs to date. We mentioned biophilic design and how it connects people and nature within our built environment and communities, and can help reduce a building's carbon footprint by using natural elements like plants, water features, and natural materials like wood. This is the Cathedral of Christ the Light in Oakland, California, and it uses biophilic design, natural materials, natural light, the use of patterns to enhance the new structure that was a replacement for the previous cathedral that was rendered unusable following the 1989 Loma Prieta earthquake. The project leaders designed this new structure with resilience in mind and a design life of 300 years. Imagine the life cycle analysis and biogenic carbon that can be credited to this building. If you recall the slide that listed best practices for sustainability, and one of those was to expose the structure, this is the Environmental Nature Center in Newport Beach, California. This LEED Platinum certified building was designed by Dan Heinfield, and he said, real sustainability is not about a scorecard, but it wears its DNA by displaying its structure rather than designing it behind additive materials. So while not awarded any points for minimizing drop ceilings or carpet, the design does expose the wood roof structure and concrete slab, not only for aesthetic reasons, but to minimize the carbon footprint with unnecessary finishes. Often in low-rise multifamily construction, the stair and elevator shafts are built first with CMU and concrete. Then the light frame wood structure is built around it. CLT, or cross-laminated timber, is a great alternative to not only eliminating a trade at this phase, but also lowering the embodied energy and materials associated with concrete and CMU. And while no building is truly fireproof, construction materials and systems can make a building fire safe. I mentioned before, we have CAD details at apacad.org for building designers and construction professionals. And this library includes several fire-rated system details, including several options to meeting IRC requirements for fire protection of I-joist floors. APA has developed several resources describing these options, and these solutions help support resiliency goals. Lightweight concrete and gypcrete toppings are routinely used as a component of fire-rated floor assemblies to provide both fire and acoustic performance in multifamily and commercial construction. This extra step can be eliminated, however, All wood floor systems can not only meet fire protection requirements, but also acoustic performance requirements. Eliminating lightweight concrete and gypcrete toppings can help speed up construction. And noise-reducing strategies in building materials can be positive to people's health and well-being, which encourages good psychological resilience. This is a detail, and there are many others available on our website. Now we'll go through some examples of good and bad resilient methods, some successful strategies and some not so successful. All this to debunk myth that there is a one-size-fits-all construction type. Rather, I like to say should be right material, right place, right installation. Resilient wood construction should resist wind, weather, seismic forces, and moisture. Wood is a resilient choice for construction. Its strength, combined with its ability to absorb stresses or impacts without weakening or degrading, makes wood a superior building material, especially in areas susceptible to severe weather conditions or seismic activity. While regionalized building codes address the necessary design requirements, APA provides additional resources detailing construction practices that help those structures perform even better against hurricanes, high winds, severe moisture, and earthquakes. This picture to the left is the result of a straight line wind event in Texas. You can see the flexible sheathing in this case did not provide racking or uplift resistance and caused whole building failure. The wind speeds were estimated here between 100 and 110 miles an hour, and that's less than the design wind speed for this area. The house on the right is a good example of fully sheathed walls with wood structural panels. Overall strength of a building is the function of all the components, your walls, floors, roof, and foundation, working together as a unit. So when an earthquake or a high wind strikes the house, the walls and roof bear the brunt of these forces. A fully sheathed wall of plywood or OSB, properly connected to the foundation below and to the roof above, is a strong barrier that resists the persistent forces of wind and earthquakes. Lab tests and field evaluations show that sheathing with plywood or OSB can help make a house 2 to 3 times more able to withstand high winds and earthquakes. This picture shows a side-by-side example of a house that has intermittent wood sheathing in lieu of continuously sheathed. On the left-hand side is rigid insulation, and on the right hand is wood structural panel. This was from an EF2 tornado in Missouri. Continuously sheathing with wood structural panels helps prevent failures like the one shown here, which was caused by projectiles that are very common in high wind events. And you can see the difference in performance between the non-structural sheathing on the left and the OSB corner bracing on the right. Projectiles cause a lot of damage in storms, and wood structural panel sheathing helps minimize that damage and potential water infiltration. We see a lot of roof failures where only part of the sheathing is removed. Like the image on the right, some of the home's roof sheathing was removed from the trusses due to a suction force. A few additional nails could have helped prevent this failure in making sure the nails actually made the connection to the supports. The detail at the bottom of this slide is from that publication I mentioned earlier, Building for High Wind Resistance in Light Frame Wood Construction. And details like this help those common failure points to perform more optimally. It's critical for roof sheathing to be fastened properly in areas susceptible to high wind or tornadoes, and especially in areas, like I mentioned, that are common failure points during storms, like at the gable end walls that are not braced, and at the rim connection between the top plate and the gable end stud going from the rim to the roof peak. Plus, at that connection in the middle image here, where that red arrow is pointing, you see the blue flexible sheathing that did not allow for a strong uplift connection or shear resistance. This would have performed better had it been fastened properly with wood sheathing that provided combined shear and wind uplift resistance. And once this gable end wall failed, it created a negative pressure, which basically blew out the roof sheathing from the trusses. Non-shear walls and gable end walls that are not sheathed with continuous wood panels can fail in high winds from the positive wind load normal to the wall. This removal can cause significant negative pressure that causes a domino effect of building deconstruction, loss of roof, wall cladding, etc. This is a detail, again, from the Building for High Wind Resistance publication. And it looks at that gable wall sheathing extending down and fastening to the upper top plate, and the wall sheathing from below extends upwards, also fastened into the upper top plate. Oftentimes, the top piece of sheathing is only fastened to the upper top plate, and the wall sheathing from below is fastened to the lower top plate. And that uplift resistance is relying solely on the connection of the two plates. And when uplift does occur, the vertically driven fasteners do not have much resistance due to that inline grain. Ideally, gable end damage will look like this. This was in Maryland, where the vinyl siding was lost, but the house performed well overall. In this photo, you see that hinge point at the gable starting to fail, but the wood structural panel sheathing on the gable end and the bracing they have at the hinge prevented water infiltration to the house and allowed the homeowners to actually continue occupying their home after this storm. Air barrier as a material, or materials assembled and joined together to provide a barrier to air leakage through the building envelope, can be a single material or a combination of materials, and its intent is to restrict unintentional flow of air through a building envelope. So a whole building barrier includes all 6 sides of the envelope. Now, these air control layers include windows, weather stripping, house wrap, wood structural panels, as demonstrated here, before the house wrap or vapor retarder was installed. This helps with heating and cooling costs, improves indoor air quality, isolates the indoor environment, and results in a durable building. The air barrier is also a key component used to prevent moisture issues as well. So another advantage of wood structural panel as an air barrier is it provides rigid, continuous base for vapor retarder to be fastened to. And while under construction, it's not flapping in the wind and or susceptible to tearing. Global warming from climate change means more evaporation, more moisture in the atmosphere, which means rainfall is intensified. And intense rainfall and changing landscapes makes for more disastrous floods. In response to increased hazards and lessons learned from recent past storms, regulatory requirements for construction in coastal areas have increased over the past decade. The way humans have developed natural landscapes both inland and along rivers and coasts means more rainwater remains unchecked and unabsorbed at the surface, turning life-giving rains into devastating floods. APA has guidance for constructing flood-resilient structures by using raised wood floor systems. A raised wood floor system is an assembly of beams and girders, floor joist, and plywood or oriented strand board floor sheathing, all properly sized, connected together, and placed on a foundation. Here's a publication, Form K110, that gives some examples of flood-resistant construction with wood frame. A raised wood floor system is designed to elevate the living space off the ground, isolating it from moisture and pests. One reason, aside from resilience, that Scott Murray elevated the home pictured on the left is for aesthetic reasons and to bring back the characteristics of historical architecture. Other reasons to build raised wood floors were it cost less to build than slab-on-grade, which can require additional fill to be brought in, and making sure that quality fill is utilized is a challenge in some areas. Raised wood floors help accommodate the scheduling of trades. For example, concrete masonry work does not have to wait on plumbing installation and inspections, which is typically the case with slab foundations. A raised wood floor system provides a practical and affordable solution for meeting code and keeping a home above floodwaters. Installation, maintenance, and modification of utilities such as water, sewer, and electrical is easy and economical compared to slab systems. Routing and rerouting of wiring for electrical, phone, television, and home entertainment is more quickly accomplished. And renovating or relocating plumbing fixtures is relatively easy and less expensive with raised wood floor systems. Constructing a pier and beam or a pile foundation, builders contend is faster regardless of the weather. A builder has several options for constructing piers when building a pier and beam foundation. The piers can rest on spot footings or a continuous footing. The placement and spacing of those footings and the piers is determined by the location of load-bearing walls and the span capabilities of the floor joists. In stem wall foundations, a continuous foundation wall around the perimeter of the home is frequently constructed of reinforced masonry or poured concrete and supported by a continuous reinforced concrete footing. Soil types can pose a challenge when constructing slab-on-grade. Expansive clays, which can crack conventional concrete slabs, and while many foundations can settle, the use of piers with a raised wood floor system makes leveling or repair simple. Repairing or leveling a cracked, damaged concrete slab can be very expensive. Treated wood piles and wood piers minimize or eliminate the use of concrete altogether. They're popular in coastal areas for acquiring necessary height, but can also be cost-effective for raising floors just a few feet. Piles are often used in soils with low bearing capacity. And for sloped lots, a raised wood floor on piers is more economical and practical than building a cut and fill slab foundation. Less soil is disturbed, reducing erosion, and the piers eliminate the need for reinforced retaining walls. With flooding, raised floors is a consideration, and FEMA has published a coastal construction manual that addresses this issue. It details different construction techniques where the first floor is raised above the design flood elevation that is based on the base flood elevation as regulated by NFIP. Engineered wood products are one popular design option that can include SCL or glulam pile caps and I-joists along with wood structural panel wall sheathing. Providing some more examples here, advanced framing, the builders can cut floor and wall framing material costs by up to 30% while reducing framing installation labor. This makes for lighter walls too for a crew to lift. Conventional three-stud corners, pictured here on the left, isolate uninsulated space in the wall. Advanced framing use strategies like California corners and ladder blocking. Ladder blocking used at the intersection of interior walls and eliminate the inaccessible and uninsulated cavities at the structural headers and are right-sized to create insulated cavity intersections. However, sometimes without proper communication to the trades, all savings realized from advanced framing can be negated by excessive and unnecessary cripple studs, as you see here. Modular design and panelized systems is also an aspect of resiliency that engineered wood products can provide solutions for. This allows for adaptability and flexibility. And in regions where we have seasonal weather that cause challenges for on-site construction, off-site panel manufacture in control facility can be advantageous for both the products and workers. Also, being that they're shippable, those panel products can offer areas devastated by natural disasters a timely delivery of systems to help rebuild faster without the need of a lot of area to mobilize for stick-built products. And finally, in our last item of the agenda is looking at APA and our resiliency goals moving forward. APA, like many organizations, are making resiliency a priority and incorporating those goals that provide solutions in achieving sustainability, energy efficiency, and durability against natural disasters when using engineered wood products. We want to be at the forefront of changes and trends, especially within the IRC-IBC and the IECC framework. Creating buildings that can withstand, adapt to, and quickly recover from various natural and human-made hazards such as extreme weather events, earthquakes, flooding, high wind events, and power outages. The goal is to use engineered wood products to support the goal of ensuring safety, functionality, and longevity of structures. And as climate change intensifies and urban centers grow, making it an essential component of future-proof construction. Our APA headquarters is a state-of-the-art laboratory for testing members' products to meet standards and to explore new ways for members to manufacture products for resiliency. This lab has a 40-foot high bay with a 4-foot thick reinforced strong floor, 10 strong wall blocks with anchors, twin 5-ton cranes, and equipment to accommodate full-scale structural assembly testing. It's built with LVL studs and purlins and glulam columns supporting curved glulam beams. It serves as a demonstration itself of wood's strength and resiliency. This is located at our headquarters in Tacoma, Washington, and is where the future of innovative engineered wood products help promulgate our commitment to the built environment that prioritizes resiliency without compromising human health or safety. And with that, and looking at the time, I want to turn it back over to Bob for any questions that we might be able to answer with the remaining time. Thank you.
Thank you, Matt and Stephanie. Before we begin our Q&A, I'd like to remind you that your feedback on today's webinar counts. The QR code shown on the screen will link you to today's survey. Just open your camera on your smartphone and a link will take you to the survey. A link will also be emailed to you in about an hour. Please take a minute and fill that out. So we do have some time left for some questions. Let me see if we can get these questions addressed. And I'll remind you, if we don't get to your question, we do have local engineered wood specialists who will be able to reach out to you, help you with your question if we don't get to it today. First question I got is, where can I find a copy of APA's resiliency policy?
It's a good question, Bob. We published our resiliency policy in June of 2024, and it can be found on our website at apawood.org. And you can click down under sustainability and it'll show up as the resiliency policy, and it'll be dated June of 2024. And it details our policy in full, including the 4 pillars and our strategic plan and operations around the policy.
Okay, thank you, Matt. I think that'll be helpful to everybody that they know where they can get that resiliency policy. Next one I have is, I know we talked a little bit about advanced framing. Does APA have resources or recommendations for advanced framing using 2x4 construction?
I'll answer that one, Bob. We do not have a resource for 2x4 because we focus mainly on 2x6 exterior wall construction.
Okay, thank you, Stephanie. Yeah, this comes up especially when we get advanced framing. I've seen this question before, but a lot of people want to know, does APA offer education or training on wall bracing?
I'll take that one, Bob. So yeah, not only do we offer it online, we have 3 one-hour sessions that go through wall bracing, and a fourth if you're in a high seismic area where you can find an hour presentation on seismic as well. But we also have a field staff across the US with the market access and development team that's there to provide in-person wall bracing education out in the field. And you can find them and the recorded presentations on our website, apawood.org.
Okay, thank you, Matt. Yeah, we do have a lot of good resources on our website. Just a reminder for you to go look at some of our other webinar recordings. Next question is also advanced framing, so this might be good for Stephanie, I don't know. When using advanced framing, do the studs, floor joists, and roof rafter trusses need to be lined up?
Well, that depends on if you keep 2 top plates or if you're going to a single top plate. If you keep a double top plate with 2x6 construction, then they do not need to line up. But if you go with a single plate, code only permits a 1-inch center offset. So just depends on that strategy.
Okay, thank you, Stephanie. Yeah, I'll just highlight, we do have advanced framing webinars available for y'all to look at too. So if you're more interested in more detailed information there, we do have those webinars available to you. Next question is, what resources does APA have on fire regarding WUI?
I'll take that one, Bob. So WUI, we don't really have a lot of resources within APA on WUI or structural fire. That's more the American Wood Council that's going to have those resources. We do reference them in some of our education, but they're the primary holder of that information, and you can find that information at awc.org. It'll come up, or the AmericanWoodCouncil.org. Either will take you to the same site, and they have different links there to their structural fire sites as well.
Okay, thank you, Matt. That was all very good information. I do see, looking at the clock, we are getting up on our hour. So at this point, I do have a few housekeeping things I want to take care of before. So, that's what we want to get to. So at this point, Matt, Stephanie, and I will turn off our cameras and we'll take care of some of our housekeeping going forward. Thank you, Matt. Thank you, Stephanie. And let me move forward. As I mentioned, APA has field staff located throughout North America. Your local APA engineered wood specialist is a free resource that is available to you for assistance on any questions you may have regarding APA engineered wood products. The individual contact information can be found on the staff contacts page of the APA website. To navigate to this page, you can go to our website, apawood.org, select the contacts on the top. This will take you to our main contact page. And if you select the Learn More options under Market Access and Development, this will navigate to our Engineered Wood Specialist page with a map showing the different territories where we have field staff. By scrolling down, you can select the appropriate region and get contact information for your local Engineered Wood Specialist. And finally, make sure that you are signed up to receive our APA Update newsletter so that you'll be notified of our next webinar, as well as future webinars and updates to APA publications and standards. To receive it, all you need to do, starting from the home page of our website, is to click Sign In on the upper right-hand corner of the page. In the menu that drops down, simply select Register. From there, you will need to let us know what you'd specifically like to receive, which in this case is the APA Update newsletter. Additionally, APA has resources to assist you at our help desk that can be reached through email at help@apawood.org or by phone at 253-620-7400. Again, thank you for attending. One last reminder, don't forget to complete the survey. I'd like to highlight 2 main takeaways we hope to leave you with. How APA trademarked engineered wood products are an effective component of resilient construction, and that proper installation is key to ensure any system built to maintain code and/or beyond code methods aim to optimize resiliency, sustainability, and occupant safety. I encourage you to download APA publications and watch other APA webinars and share with your design and installation teams to ensure effective specification and installation of resilient measures to be incorporated in buildings. Participants may review resilient building metrics to quantify resiliency. Please be sure to sign up for our newsletter. If you've not already done so, you can be notified of our next webinar. We appreciate everyone's time today and look forward to seeing you soon.